All right, so basically what we're doing now is just sort of going over what I find kind of fun little mathematical stuff. So combinatorics is something that I want to talk about. And combinatorics is pretty fun because it's got lots of stuff to do with so it's fairly simple to understand. At least it's easy to understand the question, possibly not come up with a solution, but the question is easy to understand. So it's kind of nice not having to have a high level of mathematical background and be able to do things in combinatorics. And combinatorics has a lot of input into probability and statistics, as well as graph theory, which is kind of where, so graph theory is something that I got really interested in when I was in grad school. So graph theory and probability and statistics are big contributors to combinatorics, although you can actually say it also abstract algebra and also discrete mathematics. Discrete basically meaning like we're working mostly with integers, not decimals, and not on a continuous number line, but on the integer number line. So 1, 2, 3, that sort of thing. So combinatorics. Combinatorics is a simple question. Combinatorics is basically based on the question, how many ways to achieve goal? Right? How many ways is there to achieve some sort of goal? That's the question of combinatorics. Now, what is the goal? That's kind of the open-ended thing. For example, you have 2 shirts, 3 pants, and I don't know, maybe 4 hats. I don't know. How many outfits can you do? Well, this is easy. It's 2 times 3 times 4, right? You just multiply them. So that's fairly simple. And so, but that's a real basic example of what combinatorics is. So, but what we like to do is just sort of like try to get this as simple as possible. And so let's. I just want to kind of give you another one. Let's say I have 5 different cups. 5 cups, all numbered. 1 through 5, and 5 balls. We'll do ping pong balls or whatever. Also, all numbered. Also 1 through 5. How many ways to put the ball in the cups? Well, since I've numbered them, I can tell them all apart. And since I can tell them all apart, no matter where I put them, it's a unique thing. So when I pick up ball number 1 and I say, all right, where am I going to put this? So I'm also saying there's no, there's no restrictions. I can put 5 all in 1 cup, or I can put just 2 in the 1 cup, that sort of thing. So how many different ways can I do this? Well, when I pick up ball 1, I have 5 choices. And when I pick up ball 2, I have 5 choices. And when I pick up ball 3, I have 5 choices. And so this is just simply 5 to the 5th, right? So we're going to get 5 to the 5th as how many ways to put the balls in cups. Now, what if I said only 1 in each? Well, then I pick up the ball and I have 5 choices. And then I pick up the ball number 2, but 1 cup already has a ball in it, so I only have 4. Then 3, then 2, then 1. And so that's 5 factorial, right? Nice. So that was fairly simple, right? Very easy. But now we can get way harder. And we can say, okay, look, so what if the cups are numbered, but the balls aren't? So now at this point, right? So how many ways can I do this? Okay, so So I'm just putting the balls in the cups. I have no restrictions, and I can't tell the balls apart. So whether I put the first ball in cup 1 or the last ball in cup 1, I wouldn't be able to tell. So this is a much more complicated question. And I can try to, at first I might think, okay, well, I can just do the same thing. I pick up my first ball, I put it in the cup. There's 5 different ways of doing that. But then I pick up my second ball, I put it in a different cup. And once I put it in there, I could have gotten to that, if I put here are my cups 1, 2, 3, 4, and 5. If I put my first cup here, or my first ball here, and my second ball here, well, since I can't actually tell between my first ball and my second ball, I could have put looking back at it, if I put my first ball here and my second ball here, or if I put my first ball here and my second ball here, those result in the exact same thing. So I can't tell them apart. And so they shouldn't be, I shouldn't have counted them twice, even though I counted them twice. I should have only counted that situation once. So this question gets a lot harder, but we have some methods, and this is kind of an interesting one. And this is also sort of how combinatorics work. What you really want to do with combinatorics is you want to try to take the question and sort of boil it down to a simpler idea. And if you can get a mental grasp on the simpler idea, then maybe you can answer the question. And so it's a lot of just you thinking and doing mental gymnastics to try to figure this out. So let's continue on though. So let's stick with the same problem. All right. So I've got 5 numbered cups and 5 indistinguishable balls. How many different ways can I put 5 balls into 5 numbered cups? So the cups are distinguishable and the balls are not. Okay, so how many different ways? Well, one way to think about it, and this is very interesting, one way to think about it is just think, okay, look, what we'll do is we'll just put I'm going to put a bar here, 2, 3, 4, 1. Okay, so notice, in a sense, what I've done is I've kind of designated my cups, right? Here's cup 1, here's cup 2, here's cup 3, here's cup 4, here's cup 5. Then what I can do is I can put the 5 balls in here. And let's call the 5 balls, we'll just indicate them with zeros, okay? Because they look like balls. And then the ones, we'll put these bars as ones. Now notice, so I can put so for example, one of them could be maybe 2 here, maybe none there, maybe 1 here. So we've got 3 placed and maybe 2 here. And that would be one instance, right? So what just happened? Well, really, all this was so this would mean there'd be 2 balls in cup 1, none in cup 2, 1 in cup 3, none in cup 4, and 2 in cup 5. So what did we just do? Well, basically what I did was I said, okay, look, let's boil this down to a permutation. We've boiled this question down to a permutation. I need a permutation of how many ones? 1, 2, 3, 4, 5, 6 ones, right? So I got 6 ones and 5 zeros. However, I need to start with a 1 and to end with a 1. Okay? But that's it. That's the only thing. So in reality, it's not even starting with 1. So I can place a 1 here and place a 1 here. Okay? Now, what else do I need to place? I need to place 1, 2, 3, 4, 5, 6, 7, 8, 9. I need to place 9 other things in here, right? So really, it's just a permutation of 9 things. Well, a permutation of 9 things is really easy. A permutation of 9 things is simply, okay, how would I do a permutation of 9 things? I would say, well, my first option is 9, but then I've placed 1, so 8. And then I've placed 1, so 7. Then 6, then 5, then 4, then 3, then 2, then 1. However, then you say, well, but permutation means that the order matters. Well, all I have to do now is say, well, look, what can I not tell the difference between? I cannot tell the difference between 1, 2, 3, 4, and 5. I cannot tell the difference between the 5 zeros. So since I can't tell the difference between those 5 zeros, how many orders can I put those 5 zeros in? I can put those 5 zeros in 5 factorial different orders. And I also can't tell the difference between this one, this one, this one, and this one, which is 4 lines. So I'm actually going to also say divide by 4 factorial. And this is how many different ways I can put 5 indistinguishable balls in 5 distinguishable cups. Now, the question becomes much harder if I decide to go with 5 indistinguishable cups and 5 indistinguishable balls. But let's actually finish this problem up. Sorry, I got carried away. 5 factorial cancels out with this. And so we get 9 times 8 times 7 times 6 divided by 4 times 3 times 2 times 1. 4 and 2 cancel out with the 8. The 3 cancels out with the 9, which becomes a 3. And so we end up with, looks like 42 times 3, which is 126 different ways, which is kind of interesting. I want to look at another interesting problem here. Let's see. Oh, okay. So I know what problem I want to introduce to you. And again, this is just me kind of making stuff up here. So what if you live here? And let's say it is 5 blocks to the south and maybe 7 blocks. So 1, 2, 3, 4, 5, and 7. So 1, 2, 3, 4, 5, 6, 7. So let's say you're here, and let's say, I don't know, your friend's house is over here. And every day you wake up and you guys hang out. So every day you wake up and you start to walk. And you can either choose, you can go this route maybe you go up this street, over this street, up this street, then maybe you continue to go up, but then you go over for like 3 blocks, and then you go up a block and then over. And you notice, well, every day you take a different route. How many different routes are there? Well, you can go through and count them all. It would be really horrible. But obvious. How many different routes without backtracking or making the walk longer than it needs to be? So how many different routes? Well, notice that again, it's basically the same problem, because you either can go up or you can go across, right? That's it. However, how many ups can you go? Well, you can only go 1, 2, 3, 4, 5 ups. You can only do 5 ups, and you can only do 7 across, right? So how many different ways can you basically permutate for 5 ups and 1, 2, 3, 4, 5, 6, 7. 7 acrosses. Well, that's actually not too bad, right? This would simply be, well, you've got 12 factorial divided by 5 factorial and 7 factorial. And that's how many different routes. So it ends up being a really simple problem. But because there's a story to it, we get kind of caught in the weeds. All right, so I'm going to actually post another video to sort of introduce to you a problem that I want you to work on. But this is sort of just an introduction into Combinatorics. I hope you enjoyed this. I'll talk about some more stuff about this in the future, though.